So as you can see here, my first term is the one that you are used to, right? Are you okay? So this is something that you are used to. So actually there is a relationship between this guy and this guy. We are not considering the imaginary part. So that's the idea. But the thing is, it is better for us to use the exponential form, okay? Because the form is much more simple to handle. So suppose that I have my time axis over here, and then this is my vertical axis that corresponds to the disturbance. And then I have my function over here that looks like this. So the wave here begins at t equals to 0. Am I right? This is t equals to 0. T equals to 0. Let's say if I have another wave that begins at the different time. Maybe it begins here, like that. I've got my first wave, which begins at t equals to 0, and then I have another wave that begins at t equals to, I don't know, t1. So as you can see, we have the difference in time. This is delta t. So as you can see here, if I superimpose both waves, I mean, you just add them together. So I have my wave function number 1, I add them together, okay? You need to remember this because the idea here can be applied in quantum mechanics, quantum electrodynamics that you are going to learn later, maybe during your master or whatnot. So you just add them together to get the resultant wave. But the thing is, if I have one peak and then one dip, and then the resultant is 0, right? It is very intuitive. So if you cannot understand why is it so you have to sit down and think about it for a while, okay? So that's the idea. But the thing is, we have the phase difference. Do you remember that I told you yesterday, I have my time unit, which is in second, and then I want to convert into the radian, because my brother here, my function here, only accepts radian. So what we need to do? Yeah, we multiply with the omega, correct. So you multiply with the omega to obtain the phase difference. So the phase difference is, I mean, it can be due to the space as well as the time. The example here that I'm showing you here is basically due to the time. The phase difference is due to the time. Meaning to say, I'm trying to tell you that if we have the difference in timing, so the wave will add together and becoming a different wave. But if we have the same timing, then we will have a constructive superposition. So meaning to say the amplitude will double. Let's say if I have another one which is exactly the same as the previous one, the blue color sinusoid, then the resultant is very large. So the amplitude will amplify larger. It could also be due to the space. It is not restricted to time. For example, if I have my source over here, this is my position, yes? This is my position axis. Instead of time, this is my position x. Okay, this is my position x. My position x over here, and then let's say we have source number 1, which begins over here. It is giving the wave at a specific wavelength. You know, the wavelength is distance from here to here. And then I have source number 2, which begins over here. And then if I do this, I'm going to use another color so that you can I can easily see this. So sorry, wave number 2 starts. Wave number 2 starts over here. Can you see the effect due to this? Because of the difference in the distance caused a different resultant wave. So meaning to say the behavior of the resultant wave is basically due to the difference in timing and the difference in the space. So that's the idea. So for example, I have my delta x over here. This is my delta x. Delta x. So the phase difference is given by, because we are using delta x, which is in meter. So we want to convert into radian. Then we have to multiply with our translator. which is k. So we need to multiply with k. So basically my phi now is equals to k times delta x. I need you to remember this. So the overall phase difference is just that, the summation of both. You should just sum all of them. I mean, this one and this one. And then finally, you can insert the phase difference inside your wave function. For example, my blue wave function is this. Let's say this is 1, because I have denoted 1 over here. So it is given by phi naught, which is the amplitude. This is not a wave function, yeah, just a real number, which is the amplitude. And then I have E I kx plus minus omega t plus phi. The value of phi here can be positive or negative. Okay? If there is a delay in timing, I mean, if the wave is emitted later or at later time, then the value of phi will be negative. Okay? It will be negative. The reason why it is negative is because of, you know, the direction of the wave. I've mentioned before the plus minus. How do you determine whether the wave is going forward or backward? It is because of, let's say, if negative, then you are taking the axis behind, so it looks like the wave goes towards the positive x-axis. So this is the idea. If I were to use, well, I'll just show you an equivalent example. If I use the standard wave function, which, let's say if I use cosine of kx plus minus omega t plus phi. If you have a question, why do we prefer using the exponential notation rather than the standard notation? This is the reason why. I can easily separate my phi argument here. For example, I take this E I kx plus minus omega t times E I phi. Because if I multiply this guy and this guy, I have to add the two arguments together. So I hope you get the idea. But here, do you think it's easy for me to evaluate this? I don't think so. The guy over here can be represented by using the phasor. Phasor. P-H-A-S-O-R. Phasor. So let's say if I want to draw a phasor diagram, say if I have another one, so I have my function here, which is, I have my original function, which is E I kx plus minus omega t plus phi. Oh, sorry, this is the original one. The original one should be without the phase difference. And then I have another one over here, which is my delayed function. So which is E I kx plus minus omega t plus phi. So if I were to draw this again, it is basically looks like this. So and then I have another one which is over here. So there is phi over here. So this could be either x or t. So depending on your problem, okay. So if you are visualizing this over the space, then you have to use x, or you could also use x, y, z. I mean the three-dimensional plots, which is rather complicated. But here I'm just considering the x direction. So yeah, this is my first wave function, and then this is my second wave function. Let me draw this with another color so that you can see it clearly, like that. Okay, so I hope you can relate this. So I can also rewrite my second wave function as this I kx plus minus omega t, I outside, E I theta. So you can represent this by using a phasor diagram. So if I draw this, okay, so I have a line here. This is my phi in radian, yeah. So the length of my arrow here should be, sorry, I'm using this. So the length of my arrow is phi naught. The length of my arrow is phi. This is just some representation of the wave. Okay. It is nothing physical. The x direction doesn't mean the velocity whatsoever. It's nothing physical here. Just a tool to represent the equation. So when you use the math, rather than having to find the summation, let's say if you have many waves together. So of course you can have more than one phasor. And then, for example, phi 1 is in this direction, so the amplitude is phi 0. And then this is the phase of phi 1. And then I have another one for phi number 2. So maybe you can also put it here. And then this is the phase difference for wave number 2. And then the size is phi 0, or maybe other amplitudes. So it is just like a vector diagram. So the resultant wave will be this. So the resultant amplitude is this, and the resultant phase difference is given by this. Of course, if I draw my first wave on my phasor diagram, it will be this. Because we are doing this in relative to phi 1. So the phi here should be equal to 0, because we are referencing to that particular wave. I hope you're not confused, yeah? So phi is equal to 0, so that's why we don't have any, the angle is 0, so it is along the x direction. Okay? Are you okay? I hope you're okay, yeah? This is the real, this is the imaginary axis, this is the real axis, this is the Huygen diagram, okay? This is the Huygen diagram. But the length of my phasor is phi 0, because the amplitude is psi 0. Okay, this is also psi 0, because my second wave is psi 0. So the resultant should be somewhere in the middle, am I right? Just like the vector diagram, so you draw the parallelogram. Or you can also do it this way, using the triangle. So this is my wave number 1, and then I have my wave number 2, and then I can simply draw this, and then I have my resultant wave. So the resultant is given by phi psi 1 plus psi 2. So the length, the amplitude of the resultant wave is given by the length of the resultant wave. And the resultant phase difference is given by, if I draw a horizontal line here, it's just this phi, okay? Okay, back to the yesterday's lecture. In reality, the reason why light refracts is because of the interaction between the electrons and the photon. So I have my nucleus here, I have my electrons moving around the nucleus, okay? Even though I'm using the old model of atom, so I hope you are okay with this. Actually, the electrons could be anywhere without a definite path. That is the reality, okay? But I'm drawing this because you have learned about the Bohr model, right? So it seems like electron is moving in a certain orbit, okay? But in the actual case, it is everywhere. We do not know, okay? We do not know. It's everywhere, over here, over here, over here. So, yeah. All types of light effects, for example, reflection, refraction, superposition, what else do we have? The photoelectric effects, all those all those observations are due to the interaction of electron with the photon, which is the light. So when light comes in, so depending on the situation, at some point, maybe the electron absorbs the light. It oscillates and absorbs the light. Or it doesn't absorb the light at all. It will just leave the light like that, but then it oscillates along with the light, because the light itself is an electromagnetic wave. We have the electric field component of the electromagnetic wave causes the electron to oscillate. Just like yesterday I've mentioned about my glass, okay? I have my exciter, and then I have my oscillator. So this is pretty like the photon. This is the photon. This is the photon, and then this is the electron. So the photon is inducing the electron so that the electron oscillates. So we can also assume the electron and, we can also use the oscillator model of atom. For example, we have the nucleus, which is attracting the electron, but if we bring the electrons closer, there is a repulsion force, right? So it must be staying somewhere in the middle, which is balanced. So if I push it, it will produce the force outwards. If I pull the electron, let's say if I push my electron, then the force due to the nucleus is opposing my applied force. So if I pull my electron, then the nucleus will pull the electron. So basically, it is like, let's say if I have another electron here, it's like I'm having my spring in the middle. I hope you get the idea. And then if you imagine if the electron is moving around, the nucleus, then the electron will oscillate like this. Can you imagine this? Yeah? So if you could remember yesterday, we have arrived at the differential equation to describe this, which is phi squared z. This z is the position of the electron, okay? Because I'm assuming E, the electron, is attached to a spring and attached to the nucleus. So I have my z, which is the disturbance of the position, the vertical position here, like that. But in reality, it is moving around the nucleus, right? So I hope you can imagine this, yeah? Okay, so I have my equation here, squared. Well, if, I think I've watched your previous lectures. Maybe you can also use z dot dot. But as a mathematician as well, I don't think it's my responsibility to tell you the truth. So we have to use del, because z is a function of x and t. So we have to use the right notation, yeah? So I am differentiating this with respect to t, not with respect to time, not the position. Remember this. So I have my omega naught squared z equal to 0. But I have my photon here, which is giving me some force. So the force, if you could remember, the force due to electrostatic is given by the charge of the electron times the electric field component of the photon. So the photon can be represented using E, which is E naught E I kx plus minus omega t, right? So here, the electric field here contributes to the production of the force over here. So the electric field contributes to the force. So I have my right hand side as my force, okay? So if I replace this with Q, E, then I'll have this one. And then the solution should look like this, okay? So it's QE, and then I know that my E is equal to E naught EI kx plus minus omega t, right? So it is something, it should be the same with my yesterday's demonstration about the glasses. So you replace this, so this guy becomes Q. This is the charge of the electron here. And then I have Q E naught E I kx plus minus omega t. So before I proceed, omega naught is the natural frequency of this. I mean the resonance frequency. You have learned about resonance frequency, right, yesterday? Let's say if I pull my electron downwards, then it will oscillate at a certain frequency. It is an intrinsic property of the atom. If you have argon atom, then the frequency will be different. If you use the uranium atom, then the frequency will be something different. So it is like it is moving at a certain natural frequency. And then if my electric field matches, I mean, if the frequency of my electric field here matches with the frequency of the atom, the natural frequency of the atom, so then the electron will oscillate like crazy. So let's say if the solution is Z equals to Z naught, so somewhere in the middle here is Z naught, okay? Z naught times, sorry, the amplitude, not somewhere in the middle here, somewhere in the middle here should be 0, then the amplitude is Z naught. This is negative Z naught, equals to EI kx plus minus omega t. Omega squared Z naught EI kx plus minus omega t, okay, plus omega naught. I'm substituting this here into this and then this into this. Squared times Z naught E I kx plus minus omega t. Okay, and then on my right hand side, I have this guy, which is Q, the charge of the electron. And then I have my E naught, which is the amplitude, which is the property of the photon. The brighter the photon, the higher the value of E naught. Okay, so put this inside, Ikx plus minus omega t. So the solution is given by, so I have to, I have the same term here, I have the same term here, I have the same term here, so I'll just cancel them off. Are you okay? Okay, so I'm left with omega squared z naught plus omega naught squared z naught equals to Q E naught. Are you okay? Okay, so I'm taking my z naught outside. I'm left with omega naught squared minus omega squared. And then I forgot, my apologies, there should be mass. Mass times the acceleration should be equal to the total force, right? So it should be mass over here. So this guy over here should be multiplied with the mass, okay? So I should be having my mass in front. Same goes to this one. This got minus. So I have my mass over here, which is equals to Q E naught. So finally, my Z naught, the amplitude of my electron, which is oscillating, which is dependent on omegas, omega naught and omega, which is applied to the electron. I mean the omega coming from the photon, which is applied to the electron. So omega here is the frequency of the photon, remember? And omega naught is the natural frequency of the electron string system. So if both of them match together, then the electron will be crazy. Okay? If they don't match, then the electron will follow the frequency of the applied force. I mean, the electron will oscillate according to the frequency of the photon. So here, back to my equation here, I'm left with my Z naught, which is equal to Q E naught divided by M omega naught squared minus omega squared. Okay? So I have my Z naught here, and then I have my solution, which is in this form. So the final position of my electron, I mean the position, the oscillatory motion of my electron will be Z naught, and then I replace my Z naught with my amplitude here, Q E naught over M omega naught squared minus omega squared. And then I multiply with the function here. I'm just substituting this back into the equation here. E I K X plus minus omega t. Due to the oscillatory motion of the electron, okay, due to the oscillatory motion of the electron itself, it is basically inducing another wave, another electric field. I have my electric field coming in, my photon, so the electrons is oscillating, and then due to its oscillation, it is producing another secondary electric field, meaning to say it is producing another light. So that's why in my, I gave you the Feynman diagram. So I have, this is my time axis here. This is the progress of the reaction. Sorry, the progress of the interaction. So I have my incoming photon, I have my electron coming in. So it gets excited, meaning to say it oscillates. And then it does nothing to the photon, it does nothing to the original photon. And then due to its oscillation, it is still excited, and then it generates another photon. This is the electron, right? So the combination of gamma, I mean the original photon and the secondary photon, causes the delay. But there is a phase difference between this one and this one. That's why I taught you about phase difference just now. So then, because the electron is stubborn, so there is a timing delay. Due to the timing delay, the result, I have my electron wave, I have my photon 1, this one, which is psi 1. This is psi 1. And then I have psi number 2, which is proportional to the movement of the electron. So my wave number 2, maybe it's reluctant, like that. So there is a phase difference here. So if I multiply this with omega, I have my phi. So the resultant wave, if I add both of them together, You will find that if I have my wave number 2, which is for gamma prime, the secondary photon, if phi 2 is different in phase, then the resultant wave will be backwards a little bit. So I'm using my black color as my reference to the original photon. This is my original photon, and then my original photon superimposed with the red one, and then the resultant wave will be backwards a little bit because of the superposition. In my Feynman diagram, so we have the secondary photon over here, okay, secondary photon over here. So this is corresponds, the wave function of this guy corresponds to E prime, okay, E prime, E naught E I k x plus minus omega t. But because the electron is stubborn, so there is a phase difference over here. Finally, you will find that the electric field of my secondary photon is given by Q E E naught I omega. So basically it is because in reality we have the Z over here, which is the position of the electron. So the velocity of the electron will be Z over dt, right? So I have to multiply this guy, Q E naught I omega over M omega naught squared minus omega squared I k x plus minus omega t plus phi. And then the electric field produced by the electron is equals to a constant. It is a constant. There is a constant here, constant multiplied with the velocity of the electron. Maybe the constant, I'll change this into maybe A. So there is a constant. So I have to multiply with a constant. But it doesn't matter. But it looks like that the equation here is similar. The equation here is similar to this one. This is the electric field produced by the electron. And then this is the electric field produced by, the electric field of the photon. So this one should be no negative. Should be I and kx plus minus omega t. This is the original photon. This is the electric field of the induced, the secondary electric field. Okay? Let's say if this is my medium, and then my photon coming in along the horizontal axis. So I don't want to see any refraction effect. Yeah. So this is my photon, and then this is my original photon, and then it interacts with the electron, producing the secondary. There are many secondary photons. This one, this one, this one. Okay. So there is a delay because the light moves slower inside, right? The light moves slower inside the medium. So remember that the refractive index is equals to the speed of light divided by the speed of light in the medium. So the refractive index of the medium is given by C, which is the speed of light divided by the speed of light in the medium. So meaning to say there is a delay. That's why the speed is slower. The reason of the delay is because of the interactions with the electrons. So we have at this particular point P, the electric field should be E naught E I k x plus minus omega t, just like that. But with the delay, I need to add some timing delay into this time variable. So with the delay, with the medium, there is a delay, because the speed of light is slower in the medium. So I have to add kx plus minus omega, because it is moving forward. I'm just going to use minus here. Just going to use minus. So this is my square bracket. So t plus t delay. And then finally, I'll have E naught E I kx minus omega t minus omega td. So this is the phase difference. Okay. So the velocity is given by the thickness of this, the thickness of my, this is my x-axis, the thickness of my medium. Okay, the thickness of my medium over the delay time, right? So my TD is given by delta X over V. I hope you are okay. And then I substitute this into this. I'll have E naught E I kx minus omega t minus omega delta x over V. Okay. So once we have manipulated everything, I replace this guy with Kc. Because omega equals to Kc. You have to remember this. It comes from C equals to F lambda. So C equals to 2 pi F times 2 pi over lambda. Times lambda over 2 pi. So this guy is 1 over K. This guy is omega. So C equals to omega over K. This is 1 over K. So omega equals to Kc. Substitute this, and then I'll have E naught I K X minus, this one is Kc as well, so I can bring all K's outside, Vt, and then I have minus C over V delta X. So because this is the mathematics, okay? And then after that, this is also equals to E I K. This is, this is the refractive index, C over V, X minus Vt minus N delta X. If you do the math, finally you should be having something like this. E naught E I kx minus omega t times E negative I omega, sorry, I'm not using omega anymore, I'm using K, right? So this is minus N delta X. Should be I in front. Because this is just like, the exponential. In general, if you do the math, finally you will have the form here. Okay? But the guy over here, so the exponential of, for example, exponential of y, if I expand it using Taylor series, I'll have 1 plus y plus 1 over 2 y squared plus 1 over 3 factorial and so on. So I'm just using this one to make it simple. For a small value of y, I can just take 1 plus y. I can just approximate e to the power of y as 1 over y. So I'm approximating this. So I have my e, which is equals to, finally, I have my e equals to e naught I kx minus omega t. And then I'm replacing this one with this one. So this becomes 1 plus negative I n delta x. So it will become negative I n delta x. So finally, you will have, this is the final result, which is E prime. This is the original function. This is the original photon, right? This is the original photon. So E naught E plus I kx minus omega t minus E naught E I kx minus omega t times I n delta x. Because I bring this one over here and bring this one over here. There should be E naught and E naught. Because I've mentioned that I have my I have my original photon and then I have my secondary photon. They superimpose, right? So you will see that this is the original photon and this is the photon generated by the electron. So if you compare this one, with this one, you can relate. So here we have you equate the amplitude, not the guy over here. You equate the amplitude. So you take the amplitude of the electric field. For this one, it is E, the amplitude, yeah? The amplitude is given by A QE E naught over, there is I omega here, M omega naught squared minus omega squared. It should be squared here. Okay? And then if you compare this one with this one, so the amplitude here is E naught times this, right? So the amplitude of the secondary wave is given by E naught, and then E naught I and delta x. I and delta x. So the amplitude, this is the amplitude, yeah? The amplitude, both of them are equivalent. So you will find that if you have E naught I and delta x equals to a constant, E naught I omega, there should be omega also in front here. Maybe I'm missing something. There should be omega, right? Okay, maybe I'm doing the wrong math, but the thing is, m over omega naught squared, omega squared. And then if you cancel this one, this one, this one, this one, and then n, and then you bring this down here, n is given by a constant. I mean, n is proportional to the inverse of omega squared. So meaning to say n is depending on our omegas. The refractive index depends on the wavelength of the incident photon. So the wavelength comes from here. So omega is equals to kc, right? So it should be c to pi c over lambda. So for example here, I have my prism. And then I have my light coming in, and then it refracts, and then it gets refracted again. But the thing is, it will become the rainbow color, right? So, for example, if I use the red color, will be deflected the most. Do you know the reason why? I'll show you the reason why. It is not because red color has a lower energy. No. So that, for example, there is a misunderstanding here. For example, I thought that red light refracts more because red light has low energy. If you know red light has a lower frequency, red light has lower frequency than the blue light. So I thought that because of this, the energy of red color, because energy is given by omega, right, or HF. So I thought that because of the low energy, then it will refract more. So if I take my n, it's proportional to 1 over omega naught squared minus 2 pi c over lambda. So I need to take the square. So the higher the value of lambda, the lower the value in the bracket, right? The lower the value of the bracket, the higher the value of lambda, then the lower the value in the bracket. The lower the value in the bracket means a higher this. Yeah, the lower the value of lambda, then the entire thing here will be lower, right? The guy over here is becoming lower, then the overall term here will become higher. Then it will become higher, then the guy here goes down. So that's why we have lambda. The higher the lambda, the lower the n. So that's why we have this. So my derivation is correct. I was afraid that I gave the wrong derivations. So that's why the lower the lambda, the higher the value of n. Okay, the Huygen's principle. So you know your wave fronts, the wave fronts like this. So the peak will be the wavefront. So Huygen's principle states that any point on the wavefront can be considered as a secondary spherical wavefront. That's it. For example, if I take this, for example, let's say if I have my point here, my point over here, point over here, points over here, here and here, I have to draw another spherical wavefront. So if you look based on my drawing, that I can produce another wavefront. So I'll show you in the simulator. So this is Huygen's principle. Huygen's principle states that any point on the wavefront can be regarded as a new secondary wavefront which is spherical. I'll show you. So that is the statement. It is just a statement. For example, if in the examination, it states Huygen's principle. Huygen's principle states that any points on the wavefront can be a source of the secondary wavefront, which is spherical in shape. Okay, this is Huygen's principle. So you can always find the simulator on the internet. Let's say if I change this to a straight wavefront, okay, not a spherical wavefront. So as you can see, I have my primary wavefront, which is vertical, which is it can be considered as a vertical line here. So this is my primary wavefront. My primary wavefront is over here. So as Huygen's principle states that any point on the wavefront can be regarded as a secondary source of wavefront, which is spherical in shape. So it is spherical, yeah, spherical, spherical, spherical. So you see, if you focus on this dot, it is actually emitting a spherical wavefront. Can you see that? I hope you can see that, yeah. So all of the spherical wavefronts, they superimpose. Okay, this is something that you need to imagine. It is good if you can imagine things, but all of the spherical wavefronts will superimpose, and then the section in the middle here, in between this one and this one, the section in the middle here is zero because they cancel off. But the superposition is constructive on the new wavefront. You just need an imagination, yeah?